Picture this: your build job runs for 3 minutes, installs every dependency, compiles your TypeScript, bundles your assets, and produces a beautiful dist folder sitting right there in the workspace. Job complete. Green check mark. Now your deploy job starts on a completely different virtual machine that GitHub just spun up from a clean image. It checks its workspace. Empty. The dist folder doesn't exist. It never will on this runner. This is the isolation problem at the heart of multi-job CI pipelines, and it trips up nearly every engineer the first time they try to split their workflow into separate jobs. GitHub Actions is designed around job isolation. Each job gets its own fresh runner, its own empty workspace, its own environment. That isolation is a feature, not a bug. It prevents jobs from interfering with each other and makes pipelines reproducible. But it creates a real problem when one job produces output that another job needs. Artifacts are the bridge. GitHub Actions solves the isolation problem with a mechanism called artifacts. An artifact is any file or folder that a job explicitly uploads to GitHub's artifact storage, a managed blob store that sits outside of any individual runner. Once a file is uploaded as an artifact, it's no longer tied to the runner that produced it. It lives in GitHub's cloud storage, accessible to any job in the same workflow run, downloadable by any job that asks for it by name, and even downloadable manually by a human from the GitHub Actions UI. Think of it as a shared locker room between jobs. Job A runs on runner number 1, locks its output in the locker, and walks away. Job B runs on runner 42, opens the same locker, and retrieves the files. The key to the locker is the artifact name you choose. Artifacts are retained for 90 days by default, though you can set this to as short as 1 day or as long as 400 days depending on your needs and your GitHub plan storage quota. Here's a confusion that catches almost everyone: artifacts and caches are both ways to persist files in GitHub Actions, but they solve completely different problems. A cache is about speed. You use a cache to store files that take a long time to produce but rarely change: your node_modules folder, your pip packages, your Gradle build cache. The cache persists across multiple workflow runs. On Monday, your workflow installs packages and saves them to the cache. On Tuesday, it checks the cache first and skips the install because nothing changed. That's a cache: same inputs in, same inputs out, just faster. An artifact is about data handoff. You use an artifact to pass the outputs a job produces to a job that needs to consume them: the compiled dist folder, the test coverage report, the compiled binary. The artifact exists for a single workflow run's lifetime. It's not about avoiding repeat work, it's about bridging the isolation gap between jobs within one run. The mental model is simple: cache goes in, artifact goes out. GitHub provides 2 official actions that form a matched pair for handling artifacts. The first is actions/upload artifact, currently at version 4. You call this in the job that produces the output. You give it a name, an arbitrary string, and a path, a file, folder, or glob pattern. It zips everything at that path and pushes it to GitHub's artifact store, indexed by that name. The second is actions/download artifact, also at version 4. You call this in any subsequent job that needs those files. You give it the same name you used at upload time, and the action fetches the zip, extracts it into your workspace, and your files are ready to use as if they'd always been there. The name is the contract between uploader and downloader. Get that name consistent and the rest just works. Always use version 4, it's significantly faster than version 3 for large artifacts and has better error reporting when something goes wrong. Artifacts turn up everywhere in real CI/CD pipelines. The most classic use case is build to deploy handoff. A build job compiles your application and uploads the resulting dist folder, then a deploy job downloads it and syncs it to a server. You only build once and deploy once, no rebuilding inside the deploy job. The second common pattern is test reporting. Your test job runs your full suite with coverage enabled, uploads the coverage HTML and the JUnit XML to an artifact, and a separate reporting job downloads those files to post a coverage summary comment on the pull request. This is how many popular coverage reporting actions work under the hood. Another pattern is multi-platform releases. Your build matrix compiles your application for Linux, macOS, and Windows, each job uploading its platform binary as a separate artifact, and a final release job downloads all 3 and attaches them to a GitHub release. Artifacts also appear in parallel test sharding, end-to-end test screenshot capture, and security scan report archiving. Whenever a job produces something a human or another job needs to see, artifacts. Let's look at the full skeleton of the artifact pattern. You have a workflow with 2 jobs, build and deploy. The build job runs first, it checks out the code, installs dependencies, compiles the application, and then uses upload artifact to save the dist folder to GitHub storage. The deploy job declares a dependency on the build job using the needs key. This single key does two things simultaneously. It tells GitHub Actions to run the deploy job only after the build job completes successfully, and it establishes the ordering that ensures the artifact is fully uploaded before the deploy job starts. Without needs, GitHub Actions would run both jobs in parallel the moment the workflow triggers, and the deploy job would try to download an artifact that doesn't exist yet. The needs key is not optional in this pattern. It is the mechanism that makes the handoff safe. Inside the deploy job, a download artifact step retrieves the files by name, and subsequent steps use them as local files. The upload step accepts a handful of inputs. The name input is required, it's the identifier you'll reference at download time, so make it descriptive. The path input is also required, point it at a file, a folder, or use a multi-line YAML block to specify multiple paths with one upload call. When you specify a folder, everything inside it gets included. A trailing slash is optional but makes your intent clear to anyone reading the YAML. The retention days input is optional. If you don't specify it, artifacts are kept for 90 days by default. For transient build artifacts that you only need to get through your pipeline in the next few minutes, setting retention days 1 or retention days 7 is a good practice. It keeps your storage usage low and avoids accumulating gigabytes of old build outputs. For important outputs like test reports or compliance scan results, you might set 30 or 90 days. One upload step can also accept multiple paths using a YAML literal block, list a folder on one line, a file on the next, and everything gets bundled into a single artifact zip. The download step is even simpler than the upload step. In most cases you provide just one input, the name of the artifact you want. The action fetches the zip from GitHub storage, extracts it, and places the contents in your workspace. By default, the files land at the root of the workspace, preserving whatever directory structure they had inside the zip. If the artifact contained a dist folder with index.html inside, after download you'll have dist/index.html right there in your workspace. You can override the destination using the path input path/dist would extract the artifact contents into a subfolder called dist within your workspace. If you omit the name entirely, the action downloads all artifacts uploaded in the current run, placing each one in its own subdirectory named after the artifact. This is the pattern you use in an aggregation job that needs to collect outputs from multiple parallel jobs before doing something with them. Let's walk through a complete, production-ready workflow for a Vite React application. The build job sets up node 20, installs dependencies with npm CI using the cache input on setup node to speed that up, then runs npm run build, which calls Vite and produces a dist folder with the compiled application. The upload artifact step then saves the dist folder to GitHub's artifact storage under the name React dist with a 7-day retention. The deploy job declares that it needs the build job, which creates the dependency and ordering. It then downloads the React dist artifact into a local dist directory. Notice what the deploy job does not do: it doesn't install Node, it doesn't install npm packages, it doesn't run any build tools. It only needs RSANC and SSH access, because it's not building anything, it's just deploying what was already built. This separation is one of the key benefits of the artifact pattern. Each job is minimal and focused, installing only the tools it actually needs, which makes the overall pipeline faster and easier to debug. A single workflow run can contain as many artifact upload calls as you need. A comprehensive build job might upload the build output as one artifact, the test results XML as a second, and the coverage HTML folder as a third, each with its own name and retention period. The naming convention matters because these names appear in the GitHub Actions UI and are referenced by any downstream job. The most readable convention is to use descriptive hyphenated names that indicate what the artifact contains: build output, test results, coverage report, security scan. For artifacts that are environment specific, include the environment, build output staging, build output production. One critical constraint in version 4 of the action: artifact names must be unique within a workflow run. If you call upload artifact twice with the same name, the second call will fail with an error. This is a change from version 3, which silently merged duplicate uploads, a source of subtle bugs where you couldn't tell which run's output you actually had. One of the underappreciated features of artifacts is that they're not just for interjob communication, they're also accessible to humans from the GitHub Actions UI. After a workflow run completes, navigate to your repository's Actions tab, click on the specific workflow run you're interested in, and scroll to the bottom of the run summary page. You'll find an artifacts section listing every artifact uploaded during that run, along with its size, expiry date, and a download button. Clicking the artifact name downloads a zip file containing all the files in that artifact. This makes artifacts a lightweight mechanism for sharing build outputs with teammates. Someone can run the CI workflow and a colleague can download the compiled binary or the test report directly from GitHub without any additional tooling. If you prefer the command line, the GitHub CLI's /run download command lets you download artifacts by run ID. The GitHub REST API also exposes artifact endpoints, which is how many third-party status reporting tools pull coverage and test data out of CI runs. Matrix strategies and artifacts work well together, but they require one important adjustment. Because each matrix cell runs as a separate job, each one can upload an artifact and each name must be unique within the run. The solution is to embed the matrix variable into the artifact name using a GitHub Actions expression. If your matrix is testing against node versions 18, 20, and 22, you'd name the artifacts test results node 18, test results node 20, and test results node 22. All three uploads happen in parallel, all three succeed with unique names, and a subsequent report job can then download all of them. To download all artifacts at once in the report job, omit the name input from the download artifact step. The action will download every artifact from the run and place each in a subdirectory named after the artifact. You can then use a glob pattern to reference all the XML files across those directories and merge them into a single report. This pattern is the standard way to aggregate results from parallel test shards. Artifact storage is not unlimited. GitHub's free tier includes 500 megabytes of artifact and log storage shared across all repositories in your account. Beyond that limit, storage is billed per gigabyte month. This doesn't sound like much until you consider that a busy repository pushing 10 times a day, with a workflow that uploads 50 megabytes of build output per run, with the default 90-day retention, will accumulate 45 gigabytes of stored artifacts. The most effective lever is the retention days parameter. Transient build artifacts that only need to survive long enough for the deploy job to download them can be set to 1 or 3 days. Test reports that you might want to reference when investigating a production incident probably deserve 30 days. Compliance-related outputs like security scan results might need a year. You can also set a repository-wide default retention at settings, then actions, then general. Individual workflow settings override the default, so you can set a conservative default of 7 days for the whole repo and then explicitly extend it for the artifacts that matter. The standard artifact pattern works within a single workflow run, one workflow, one run, multiple job sharing files. But sometimes your architecture calls for separate workflows, for example, a CI workflow that runs on every commit, and a publish workflow that only triggers when CI passes on the main branch. To download an artifact produced by one workflow in a different workflow, you use the workflow_run trigger combined with the GitHub REST API's artifact endpoints. The workflow_run trigger fires when a specified workflow completes. You can guard the consuming workflow with an if condition to only proceed when the triggering workflow concluded with success. Then, instead of using the standard download artifact action, which only works within the same run, you use the GitHub script action to call the REST API, list the artifacts from the triggering run's ID, find the one you want by name, download it, and extract it. This is more involved than intra-run artifact sharing, but it's the correct pattern for true cross-workflow data passing. One important gotcha: workflow_run always executes in the context of the base repository's default branch, not the triggering branch, which has significant implications for what secrets it can access. Time to lock in the key mental model from this chapter. The scenario: a build job compiles your application into a binary. A test job on a separate runner needs that binary to run integration tests against it. Should you use cache or artifact? The answer is artifact, and the reasoning is important. Cache is for reusing unchanged inputs across multiple runs. You'd use cache to store your node_modules folder because those files are inputs to the build step and they rarely change. You install them once, cache them, and skip reinstalling on subsequent runs until your lock file changes. The compiled binary is the opposite: it's an output, not an input. It's produced by the build job and consumed by the test job within a single workflow run. That's exactly what artifacts are designed for. Cache would technically work, you could save and restore a binary via cache, but semantically it's wrong and you'd be fighting the tool's design. Artifact is the right abstraction. Use upload artifact in the build job, use download artifact in the test job with a matching name, declare needs in the test job, and the binary flows from one runner to the other transparently.